Are we going to start? Okay. So we're very happy to have Elad Paran from the Open University of Israel, who will be speaking on algebraic geometry over division rings.
Thank you very much. First, let me just make sure that everybody can you see the slideshow?
I can.
Okay, so that's a good indication. Okay, so thank you for the kind invitation to speak in your seminar. I will discuss a topic that has gained traction over the past 6 or 7 years concerning the foundations of algebraic geometry over division rings. And I should preface and say that throughout this talk, all rings will be assumed to be associative and unital, of course, though usually non-commutative. However, you'll see that basically every question we'll discuss could potentially also be studied in the context of non-associative rings over the Octonian algebra or over general non-associative division rings. So my hope is that perhaps some of the attendees of this seminar would be interested in extending this line of study to the non-associative world. So that's my motivation in this talk. Okay, so having said that, let me begin with some very classical 19th century motivation. Consider the ring of polynomials in n variables over the complex numbers. Given an ideal J in this ring, we can associate to it the zero locus, the set of points where every polynomial in the ideal vanishes. And conversely, given a set of points in the affine space, we can associate the ideal vanishing of all polynomials vanishing everywhere at Z. So on the one hand, we have these algebraic objects, these ideals, and on the other hand, you have these geometric objects, these sets of points, and we have some correspondence between the two. And the most basic question of algebraic geometry is what happens if you try to go back and forth between algebra and geometry? In other words, what is I of Z of J? And the famous answer is, of course, given by Hilbert's Nullstellensatz, which states the following. So I of Z of J is the radical of J. And we can describe it explicitly at the set of roots of elements in J, or implicitly as the intersection of prime ideals contained in J. And so we have an explicit form and an implicit form, and these two together are sometimes known as the strong form of the Nullstellensatz. We also have the so-called weak version, which simply states that if you have a proper ideal in this ring, then you can find a common zero to all elements of J. Now, the terminology is slightly misleading because on the one hand, you can easily see that just formally the weak version is an implication of the strong version, but also the other way around is true. There is a trick, there's a famous trick to deduce the strong version from the weak version, and we will discuss that later. So it's just one theorem. Now, if you were at the special case where n is 1, where you only have one variable, then of course we have a principal ideal domain, and in this case, the ideal J is generated by a single polynomial of positive degree. So in this case, the statement is simply that there is a zero to this single polynomial, which is just the fundamental theorem of algebra. So one way to think about the Nullstellensatz is as a higher dimensional fundamental theorem of algebra. Okay, so this is very, very classical. Let me jump forward to maybe 50 years to 1941. Consider now the quaternion algebra, the classical one, with the usual product rule. Then we have the following theorem. If you have a polynomial over this algebra, where the coefficients are written on the one side of say, the left of the monomials, then you can find a quaternionic zero of such a polynomial, if it's a non-constant polynomial. So we basically have a fundamental theorem of algebra over the quaternions. This was proven by Niven for odd degrees, and then by Nathan Jacobson, for the general case. And I shall refer to it as the Niven-Jacobson theorem. So this is 1941. Okay, so I think you can guess where I'm going with this. If the classical Nullstellensatz is a higher dimensional fundamental theorem of algebra. And we do have a fundamental theorem of algebra over the non-commutative quaternion algebra, then you can ask, do you also have a higher dimensional version of that? In other words, do you have a quaternionic Nullstellensatz? And this question arose in some pretty random conversation between Gil Alon and myself sometime, I think it was 2019 or 2020, something like that. And we were wondering about it, and we couldn't see an immediate answer. And our first expectation was that this should be well known, because you could have asked and probably should have asked this question in 1941, following the theorem of Jacobson. Although people may have been a bit preoccupied at that particular point of history, but still, maybe a few years later, somebody should have considered this. But to our surprise, when we started to search the literature, we could not find an answer. And so we started to try to work it out for ourselves. And initially we thought, okay, this is just going to play out like the classical complex Nullstellensatz. But things turned out to be much more interesting than that. So first we need to formally describe the question. So first we consider the ring of polynomials in a central variable over the quaternions. So when I say a central variables, I just mean that additively it's just the usual ring with the usual product rule. And if you apply the usual product rule, it just follows that if you multiply a variable x by a constant a from the right, it's just ax. So from this, it's immediate that the variable commutes with everything. So the variable is central, and it is well known that this is a left and right principal ideal domain. So if you have, say, a left ideal in this ring, then it is generated as a left ideal by a single polynomial. And it is well known, it is a classical theorem of Gori from 33, that this is a non-commutative unique factorization domain. So here, uniqueness is up to order and up to similarity. So two polynomials are called similar if the corresponding quotient modules are isomorphic as our models. In the commutative case, this is just equivalent to saying that the polynomials are associates, but in the non-commutative case, it's somewhat more complicated. Still, it's a very nice theorem generalizing the classical theory. Now, if you have such a polynomial and you say you have a quaternion z, then you can simply plug it in, you can substitute, and you get some quaternion. But here you have to be a bit careful, and you need to note that substitution is not a homomorphism. It is true that if, say, g vanishes at z, then also fg vanishes at z for any f, but the converse need not be true. Substitution is only a half homomorphism, meaning that the kernel is only a left ideal in general. So for example, if you consider x minus I, x minus j, and you multiply them, you get this polynomial, and then you try to plug in I, well, visually you might think, well, this should vanish, but no, if you plug in I, you just get minus minus k plus k. So you get 2k, which is not zero. On the other hand, of course, if you compute fi times gi, you get zero. So this just to show that substitution is not homomorphism. You do have a very nice substitution formula, which states that if g does not vanish at z, then the value of the product at z is f of z conjugated by g of z times g of z. Now, similarly, if you have, say, n variables, then you can construct the ring of polynomials in n central variables over the quaternion algebra. So here, again, it's just the usual product rule where the j and I are multi-indices. But now you have a problem with substitution. So consider, say, the polynomial xy. Because our variables are central, this is the same as the polynomial yx. Now, what happens if you try to plug in ij? Well, if you write it with the first presentation, you get ij, which is k. But if you write it with the right presentation, you get ji, which is minus k. So this is just to show that substitution is not everywhere well defined. Another way to see it is that if you have a point in the quaternionic plane where the coordinates do not commute, then the left ideal generated by x minus I, y minus b is not actually a proper left ideal, but rather the whole ring. You can easily check this. On the other hand, if you have a point where the coordinates do commute, then FAB, if you just plug it in, it is well defined, and it is the unique quaternion such that F minus this quaternion belongs to this left ideal, and in this case, it is a proper left ideal. This leads me to the following definition. We shall define the quaternionic central affine space to be the set of tuples of n quaternions where all of the coordinates commute. So for example, j plus k minus j plus k is a point in this space, but I and j is not. Now you can easily see that if you have a point in this space which is not a real point, then the subalgebra of the quaternions generated by the coordinates over R is just a copy of the complex numbers. So topologically speaking, you can think about this space as formed by gluing infinitely many copies of C to the n, all intersecting at R to the n. So if you want to have a picture in mind, this should be the picture. So this is the set of points where substitution is well defined. Okay, so as noted, the kernel of the substitution map is only a left ideal. And more precisely, you can check that this kernel is that the ideal generated by x1 minus a1 up to xn minus an is the kernel of the substitution map on the corresponding point of the central affine space. Okay, so what we see here that in this geometric context, we need to study one-sided ideals. It's not enough to consider two-sided ideals. Of course, we would have liked that. It would be technically easier, but we would simply miss out on a lot of the geometry. We would simply miss out on a lot of points. So we cannot do that. We have to consider one-sided ideals. Now, there are many papers, quite a few papers, studying properties of two-sided ideals in such rings. And that's not good enough for our cause. But there is one paper I want to note that does focus on one-sided ideals. It's a paper from 1978 by Amitsur and Small called Polynomials over division rings. And the main result of this paper is the following. If you have a division ring D and a maximal left ideal in the ring of polynomials in n central variables over D, then the quotient module is finite as a lefty module. And Amitsur and Small call this a Nullstellensatz over division rings. However, I would argue that the terminology is not quite fitting. I think this is closer to Zariski's lemma over division rings. In the commutative case, it is true that the Nullstellensatz is an immediate implication of Zariski's lemma. In the non-commutative case, it's not so straightforward. Nevertheless, whatever you want to call it, it is a very nice result. However, we are interested in the specific case where D is the quaternion algebra, and in this case, we can say much more. So first, we have the weak Nullstellensatz, which simply states the following. If you have a proper left ideal J in this ring, then you can find a common zero in the central affine space for all polynomials in J. So this is exactly what you'd expect. You just have to restrict yourself to the right space. More precisely, the maximal left ideals in this ring are exactly in correspondence to the points in the central affine space. And in the special case where you only have variables, where you only have one variable, you simply recover Jacobson's theorem that we mentioned at the beginning. Okay, so we have the weak version. What about the strong version? Okay, so consider a left ideal J in this ring. We can define the zero locus Z of J to be the set of points in the space where every polynomial in J vanishes. And conversely, given a set of points, Z, we can associate the ideal of vanishing, which is only a left ideal in this context. And once again, we have the question, what happens if you go back and forth between algebra and geometry? So what is I of Z of J? And if you want to guess, your first guess is going to be that This is just the set of roots of elements of J. Okay, so let's consider this. How do you prove it in the complex case, in the commutative case? In the commutative case, you have a very cheap trick to deduce it from the weak version. So we can review the whole thing in one slide. This is the so-called Rabinovich trick. You consider an ideal J in this ring, and you take a polynomial, a non-zero polynomial that vanishes everywhere at Z of J. We want to show that this F belongs to the radical of J. So the trick is to extend to a higher dimension. We add one variable y, and then we consider the ideal J prime generated by the elements of J and 1 minus yf. In this ring, R prime, which is obtained by adding one variable. Now, by the definition of this polynomial f, it is immediate to see that there is no common zero to the elements of J prime. And hence, by the weak version, we know that J prime is the whole ring. Okay, so we can find such coefficients Ji and Hi in R prime and J respectively, such that you get this equation giving you 1 on the right-hand side. And now the trick is to simply substitute y goes to F inverse over the quotient fields. This gives you this equation, where on the left-hand side, you only have some powers of F in the denominators, and then we can simply multiply by a large enough power of F to get the following equation, where Hi are elements of J, and the Gi bars are elements, just some coefficients, which are now polynomials. And this shows you that F belongs to the radical. Okay, so now you can try to imitate this idea in the quaternionic case, but the problem is that you can only carry out the first part. You can't increase the dimension by 1. You can try to do the same thing, but then you cannot substitute and translate the information back down to the space where you started with. The point is that substitution is not a homomorphism, so you cannot translate the information. And at first glance, this may seem like a technical problem, but it is not. It is actually a meaningful problem. And we can just give you a concrete example how the statement simply fails in dimension 1. Consider the polynomial we had in the beginning, xi minus xj. Then you can just check that it emits a unique zero, namely j. So we saw this in the beginning. This polynomial does not vanish at I, but the only zero is j. So this just means formally that x minus j belongs to the ideal of vanishing at z of the ideal generated by f. But then you can just check by hand that no power of x minus j belongs to this ideal, which means that I of z of j is not the set of roots of elements of j. Okay, so when you see this, then immediately you ask, okay, so it's not our first guess, then, well, what is it? What is this ideal? It has to be something. We should be able to describe it. Okay, so to answer this question, we need to say a few words about the notion of prime ideals or one-sided prime ideals in non-commutative algebra. So first we have the following definition. A left ideal I is called prime if given the product of two left ideals A and B. In I, it follows that A belongs to I or B belongs to I. And then an ideal is called strongly prime if it satisfies the commutative definition that if AB belongs to I, then one of the elements belongs to I. And it is well known that in the non-commutative context, the second definition is too restrictive. And so usually the first definition is the one that is prevalent in the literature. But neither of these definitions is the one we worked with. The definition we want to work with is the following. We say that left ideal J in a ring R is completely prime if whenever AB belongs to J and additionally J absorbs B from the right, then it follows that A belongs to J or B belongs to J. This is an odd-looking definition if you see it for the very first time. It was introduced in a PhD thesis of Manuel Reyes, who was a student of Lamb at Berkeley at the time. And what Reyes shows in his thesis is that if you try to work with this definition, then certain, just one moment, my dog, I need to get my dog away from me. Luca, Alta, Alta. Okay, that's it. If you work with this definition, then certain theorems in commutative algebra extend beautifully to non-commutative algebra. I will not get into specifics, but if anybody is interested, I recommend having a look at Reyes's thesis. It's just a beautiful PhD thesis. So it turned out that this is also exactly the notion that we want for our work. And what we will do is we will define the radical as a left ideal J in our ring to be the intersection of all completely prime left ideals containing J. And now I can tell you finally what is the strong Nullstellensatz. If you have a left ideal J in this ring, then I of Z of J is the radical of J as we have just defined it using this notion of Reyes. So you get a theorem which is exactly like you'd expect, but only for the implicit version of the Nullstellensatz. We don't have an explicit version, and I'll return to that in a moment, or we didn't have at the time. Okay, so how do we prove this? Now, in the complex case, there are several kind of quick and dirty ways to prove the strong Nullstellensatz, but all of them fail in our setting, essentially for the same reason I showed you in that one example with the Rabinovich trick, because substitution is not a homomorphism. All of the tricks, all of the cheap tricks fail. So we have to go through a somewhat more conceptual approach, which is the Jacobson approach to the Nullstellensatz. And the Jacobson property says the following. So recall that if you have a commutative domain, we say that it is a Jacobson ring if every prime ideal in this ring is an intersection of maximal left ideals. And then there is the theorem that any ring of the form kx1 up to xn, where k is a field, is a Jacobson ring. You can say something more general, but for this talk, this is enough. And what we will do is we'll show that the ring R, our ring, the polynomial rings over the quaternions, that it satisfies a Jacobson-like property, namely that if you have a completely prime left ideal in this ring, then it is an intersection of maximal left ideals. So to prove this, we need a few claims. The first one is that, okay, so let us denote by R prime the center of this ring, which is just the ring of polynomials in n variables over the real numbers. Then we have the going up theorem, which states that if you have a maximal left ideal in just a maximal ideal, it's commutative in R prime, then there is a maximal left ideal M lying above it in the ring R. That's one. The second property is that any maximal left ideal is in particular a completely prime left ideal. And the third is the so-called incomparability lemma, which simply states that if you have two left ideals P containing Q in R, and P happens to be completely prime, then if the contraction of these two ideals agrees on the center, then the two ideals are already the same. Okay, so the first two properties are easy to prove. The third one is remarkably tricky. In the commutative case, it is quite easy to prove it. You simply go over to the quotient rings and it follows from there. In the non-commutative case, it is much more complicated, and there is a beautiful proof that my colleague Gil gave, which uses some explicit polynomial identities of the quaternions. I will not have the time to show it. I'll just mention that that is the technical core of the entire proof. Okay, but let us just believe these three lemmas and see how to prove the Nullstellensatz. Or first, the Jacobson property. So we start out with the completely prime left ideal, P, and then we contract it to the center. We call that little p. Now, since the center is a Jacobson ring, we know that this P is the intersection of the maximal left ideal in our prime containing P. Now, by the going up lemma, every one of these maximal left ideals lies beneath a corresponding maximal left ideal M in the ring R. And then you consider the intersection of all of these ideals Q. This gives you a left ideal Q containing P, such that both of them agree on the center. It's just the ideal little p here, which means by the incomparability lemma that these two ideals P and Q coincide, which means that P itself is an intersection of maximal left ideals. So from the incomparability lemma, the Jacobson property follows. And now, given this, we can prove the strong version of the theorem. So first, by the weak Nullstellensatz, we know that maximal left ideals correspond to points in the central affine space. So this means that I of z of j is just the intersection of the maximal left ideals contained in J. On the other hand, we know that every one of these ideals is in particular a completely prime left ideal, and moreover, every completely prime left ideal is the intersection of the maximal left ideals containing that. And this means that the intersection of all the completely prime left ideals containing J is the same as the intersection of the maximal left ideals containing J. Which means that the radical of J is, as we have defined it, the I of z of J. And that's the proof of the strong version. And I basically showed you the whole proof modulo that key technical claim, which I will not have the time to show. Okay, so that's this theorem. Now, I should note that there was a theorem that was proven a few years later by Jakob Simprick, and he looked at our work and he asked himself, can we replace completely prime left ideals by just prime left ideals? And even though in general the notions are not the same, for this particular theorem it works. You can define the radical by using prime left ideals rather than completely prime left ideals. However, his proof relies upon our theorem. It's not a direct proof. So one could still argue that maybe completely prime left ideals is the more natural notion, but now it's a philosophical question. It's not clear what is the more natural question, and it is a very prudent question, very important question, and we will revisit it in a moment. Okay, and here prime is in the sense that we had before. Okay, now all of this just gives you an implicit version of the description of I of 0j. And you could ask, is there an explicit version? Now, we know that the more natural one, the one that you would hope, does not work. But you can ask, well, do you have another one? A more complicated one, potentially. So we thought about it at the time, and when we wrote the first paper, we couldn't see how to prove it, how to establish such a description. But then Masoud Aryapoor found such a description, and I'll describe it right now. You start out with the left ideal J in this ring. We have this theorem of ours, and then you can describe the radical as follows. It is a set of all polynomials such that for any quaternion A, you can find a power n such that AF to the n belongs to the following left ideal, J plus JAF up to JAF to the n. That's a description. It is more complicated, and it's quite annoying that you have this restriction that you need to have this condition being satisfied for all quaternions A. You cannot replace it just with A equals 1. There is a counterexample to that. So this is simply the best that you can do. So it is unfortunate, but that's the mathematical reality. It's just more complicated than you would like, but it is what it is. That's the theorem. And I should mention that the way he proves it is very nice. He basically says, okay, we saw that the Rabinovich trick doesn't work, but Aryapoor says, I want to force the issue. And he's doing exactly the same trick. And when he comes to that point where substitution is not a homomorphism and he cannot just translate the information back down, then he relies upon the substitution formula we had at the beginning of the talk. And he says, okay, we have this more complicated formula. What does it give me? And then he follows the information. What does this formula give? And it turns out that it simply gives this complicated description, and that's the way he proves the theorem. It's very nice. Okay, this raises some immediate questions. So first, can this description work for arbitrary division rings, or um, can this description work at least for algebraically closed division rings? And I should point out that there are other examples of algebraically closed division rings other than the quaternion algebra. Most notably, a very famous one due to Makar Limado from 1985, which I will not get into. And this is somehow an important question. The point is that in classical algebraic geometry, you do not just develop the theory over the complex numbers. You develop it abstractly over algebraically closed division ring. I'm sorry, over algebraically closed fields. So now we would like to do the same. We would like to develop the theory abstractly over all algebraically closed division rings. But it's not clear if we can do that. Can we develop the theory abstractly, or are we somehow forced to limit ourselves to certain division rings, such as the quaternion algebra? We don't know the answer to this question. And more generally, you can just ask, do you have a general description of the radical for a left ideal J in arbitrary ring R, an explicit one? I do not know, and somehow I suspect that it's hard to come up with something like this. Okay. So now, moving on, so we have this Nullstellensatz, we have this foundation, and you can start to ask yourself, can you develop algebraic geometry? So you can take this in many ways, but for example, can you develop a theory of height or dimension in this context? So in classical theory, you measure height in algebraic geometry using chains of prime ideals. So it sounds reasonable that here you should do it using chains of either prime ideals or completely prime ideals, left ideals. It's not clear which one, but we would like to know if such chains of prime ideals or completely prime left ideals behave in a similar fashion to their behavior in the commutative case. So the starting point is the same for both completely prime left ideals and prime left ideals, which is what happens with maximal left ideals. So now let me ask a concrete question. Do maximal left ideals contract to maximal left ideals? So just for simplicity, consider two variables. If you have a maximal left ideal M in dxy, is the contraction to dx a maximal left ideal in dx? So I was wondering about this. I couldn't see an immediate answer, so I started to search. And it turns out that this question was asked a long time ago in the same paper of Amitsur and Small I had shown in the beginning of the talk, the Nullstellensatz over division rings. So the main lemma, the key lemma in the proof of their theorem was the following. If you have a maximal left ideal in this ring, then if you intersect it with, say, the ring of polynomials in one variable, it is a non-zero ideal. Now, if your ring D happens to be a field, then it immediately follows that this ideal is prime and hence maximal. But in the non-commutative case, it's not so clear what's going on. And Amitsur and Small write the following. We remark that we are unable to show that maximal left ideal in this ring intersect with smaller polynomial rings in maximal or even semi-maximal left ideals. Now, semi-maximal left ideals simply means that it is an intersection of finitely many maximal left ideals. So they raise two questions here. is maximality preserved and is semi-maximality preserved. The second of these questions was answered a year later by Robson and Small. They showed the following. Okay, so this is the main proposition in their paper. They show that if you have a semi-maximal right ideal, it contracts to a semi-maximal right ideal. So they use right terminology, but of course it's the same with left. So this answers the second part. They do not answer the first part. Then there was another paper by Resco that gives some related results, which I will not get into. But he also notes that it remains unknown whether one-sided maximal ideals contract to maximal ones. And then I couldn't find any paper concerning this question up until 1995, where we have this paper by Louis Rowan. And in this paper, he writes that the answer is negative. So I will not read the whole area around this sentence, but he essentially writes that the answer is negative and that there was a counterexample recently showed by Amitsur and Small. So Roman writes that Amitsur and Small gave a negative answer to their own question 17 years later. So I started to search for this answer in papers from around that period of time, and I could not find it. So I simply wrote to Rowan and asked him, well, what did you mean by this sentence? And understandably, Rowan could not remember. It was 30 years ago. Now, it should be noted that Amitsur had died at the end of 1994. So maybe this has something to do with this. Though, of course, if they had an answer, then Small could have published it after Amitsur's death. But then I just wrote to Small upon the suggestion of Owen, and Small, who is alive and well and active, said that as far as he can remember, they never answered this question. So it's very, very funny. It's not clear what happened here. Either they had an answer and somehow maybe having to do with Amitsur's death, that answer was not published and forgotten. That's one option. Alternatively, it could be the case that maybe there was some miscommunication at the time between them and Rowan. I'm not sure what happened. Anyway, to make a long story short, I had to work it out for myself, and it turns out that there is indeed a counterexample. And I will give you there are many counterexamples, but I will just give you the first example I could come up with, which is the following. You take a field K, and then you take an automorphism sigma of K, and then you consider the field of the skew field of Laurent power series over K. So what does this mean? So additively, it's just the usual field of Laurent power series. But the multiplication rule is determined by the fact that if you multiply the variable t by a constant a from the right, you get a sigma times t for any a in k. This rule is known as the Hilbert twist. Okay, and it is well known that if you define multiplication via this rule, then you get a division ring. And now what we do is we choose an element A in K, which is not fixed by sigma, but is fixed by sigma squared. And then we consider the following ideal, the left ideal generated by x plus t, x minus t, and y minus a. You can check that this is a maximal left ideal. This is not a trivial check, and it is maybe somewhat surprising. First, it's not even trivial that this is a proper ideal, but it is. You have to check this. But once you check that, it may be surprising that this is a maximal ideal because when you just visually look at it, you might think, well, this is properly contained in the ideal generated by x minus t, y minus a. But the point is that the latter ideal is the whole ring. So this follows from the way I chose this constant a. But then if you intersect this ideal m with the polynomial ring dx, you get the ideal generated by x plus t, x minus t, and this time it is not a maximal left ideal because it is properly contained in the ideal generated by x minus t. So that's the counterexample. So the answer is in general negative. However, there is some good news. The good news is that you cannot build a counterexample with any underlying division ring. And in particular, if you take the quaternion algebra, then the answer is positive. So maximal left ideals contract to maximal left ideals. So if we want to develop algebraic geometry over division rings, then at least this initial behavior is as you want it to be. So this is good news. This leads me to the following definition. Consider a division ring D. We should say that D is an Amitsur small ring if maximal left ideals contract to maximal left ideals for any k smaller than n. And on the other hand, we should say that D is a Nullstellensatz ring if the maximal left ideals in this ring correspond to points in the corresponding central affine space. So a Nullstellensatz ring is a ring that satisfies the conclusion of the weak Nullstellensatz. And then we have the following theorem, which is joined by Adam, Chapman, and myself from 2025. If D is algebraically closed, then D is a Nullstellensatz ring if and only if D is an Amitsur small ring. Okay, so now you can ask the following: are all algebraically closed division rings Nullstellensatz rings or Amitsur small rings? Or more generally, can you characterize the Amitsur small rings? And we had some partial results about this from last year in our paper, and then there was another paper that gave some additional partial results. I will not get everything. I will not describe everything. I can just give you now the whole answer, which is a theorem I was able to obtain by working with the AI very recently, actually in preparation for this talk. If you have a non-commutative division ring of finite dimension over its center, then D is Amitsur small if and only if D is algebraically closed. And this is also equivalent to saying that D is a quaternion algebra over a real closed field. So we have a complete answer in the centrally finite case. In the non-centrally finite case, it's not clear what happens. And in particular, I don't know what happens for the Makar-Limanov ring. And again, this is very important for the reason I pointed out in the beginning. We don't know if we can describe, if we can develop the theory abstractly, or are we somehow limited? Okay, this is where we're at now with this point. Now, if I have a few more minutes left, let me tell you one last part of the story. There are others, but I just want to say one more thing. So we have the following paper by Gori, Sarfatti, and Vlacci. And what they did is the following. They looked at our paper and they said, okay, we had this restriction for commuting points for the central affine space. And they said, we don't like this. We want to try to force the issue and have substitution be defined everywhere at, say, the quaternionic plane. So how do we do that? Well, if you recall, the problem was, just one moment, my dog needs to get out. 1 second. Sorry. Okay, so what was the problem? The problem was that it's not clear how to evaluate the polynomial, say, xy. Well, the problem was that if you evaluate it when you view it as xy or as yx, you get a different answer, say, at the point ij. Well, they said, let's just completely ignore this problem by fixing an ordering of the variables. Just fix some order. Say x smaller than y. And then the definition is now well defined. You can just arbitrarily decide that the value would be k, and so on. And if you do this, then substitution is now defined everywhere. However, this comes at a cost, at a loss of structure. Now, the kernel of substitution map with this definition is not even a left ideal. So this is a problem. But the good news is that if you have a left ideal J and then, okay, so now we have to consider two kinds of sets of zeros. One is I will override the notation I had before and I will write ZC of J to be all points in the central affine space where the ideals of J vanish. And I'll define Z of J to be all points in H square where the ideal, where every element of the ideal vanishes. Then you can ask, well, simply what is I of Z of J? The question is well defined. Well, it turns out that in this case, I of Z of J is a left ideal, which is not a priori clear, but it is a left ideal. Moreover, the main theorem in their paper was that this ideal is exactly the ideal of vanishing at ZC of J, which is the radical of J as we had defined it. So what this shows you is that, yes, you can enlarge the space of definition, but it doesn't actually give you any richer geometry, at least not in dimension 2. Okay, now concretely, the point of their proof is that if you have a polynomial in two variables that vanishes everywhere at ZC of J, then it follows that it already vanishes everywhere at Z of J. This is not obvious, and this is the main point of their paper. However, their proof was specific to the case of two variables, and they asked, is this true for any number of variables? And we had shown later, Gil Alon and myself, that the answer is yes. And then later on, a couple of months later, Gori, Sarfatti, and Vlacci also gave a different proof of the same result. So all of this is to show that you do not get anything new from enlarging the space, but technically it might be more convenient to do it, and you might want to develop the theory in that way. Now you can ask, does this hold if you replace H by a general algebraically closed division ring? And the answer is we do not know. I should point out that it does not hold over arbitrary division rings, and there is a counterexample by Adam Chapman. Okay, so just to summarize everything, you have a lot of technical problems, but eventually the commutative theory naturally extends to division rings. Establishing the foundations is not so straightforward. I would hope that eventually we could develop a theory which just mirrors the complex theory, or maybe even the whole theory over algebraically closed fields. But at this point, even the foundations are not quite clear, for example, because of the issue with algebraically closed division rings that I touched upon several times throughout this talk. So we have made a lot of progress by several groups of people over the past 7 years, but there is still much more to be done. However, I think that because we now work with AI, then we can make progress in a more rapid pace, and I think that I would hope that we could develop the theory in a reasonable time. Okay, so this is all I wanted to say.
Thank you, Elad, for the very interesting talk. Are there any questions? Okay, so while people are thinking about the questions that they can raise, I have a small question. So you mentioned in the beginning that some of the main themes may extend to octonions. Do you have any idea how it should be done? I can't imagine how ideals should work over the octonions, right? Because
No, I don't have any idea how this should be done because I really know very little about non-associative algebra. And if you do not know, then what could I hope for? But maybe somebody here could take up the challenge and try to work it out. There should be something, right? I should note that we did look into it, and there is a version of the fundamental theorem of algebra over the octonions. So the
Right.
starting point for everything is there. So the question makes sense, and now one has to figure out what are the right notions to work with.
I have actually another question, which concerns motivation in some sense. When you consider equations over fields, especially when you think about equations, the kind of ideals that these polynomials generate, they usually correspond to interesting varieties, and these varieties give rise also to, quotient fields of the corresponding of the corresponding ring. And uh, do you have any motivation in this sense? Like if you take, for instance, an equation over a division ring and this equation has no zero, what would you get by introducing a root to this thing? Is there any Galois theory
Oh,
behind it? Or...
I do not know. There are many problems. Let me start by you mentioned varieties. So there's a problem already even just defining varieties because if you try to do it like in the complex case and you try to develop a say a Zariski's topology or something like that, it just doesn't work. So you have a problem with unions. Um, so I don't know, but there is a paper which I have not yet read, a recent one, I think it was by two of the three, Gori, Sarfatti, and Vlacci, and somebody else. I'm sorry, I don't remember the name. Where they deal with this, where they try to develop some theory of varieties, and then you want to study singularities. But I don't know. You raise a valid question. I do not know the answer yet.
Okay. Any other questions? If not, then let's thank Elad again. Thank you, Elad.
Thank you.
I guess we'll resume next week.